Hi everyone and welcome to my desk. My name is Bill and today we'll look into this real-time clock modules that you can use with Arduino, and we'll see how we can connect them, how we can interface them, and how to properly set and read the clocks. A real-time clock is usually an IC that can be connected to a backup battery, and its sole purpose is to keep track of the time. In my case, I have the DS1302 IC, which other than providing clock data and keeping track of time, can also trickle charge the battery that it's connected to. The module consists of a crystal that's running on 32,768 Hertz, and this is the right frequency for keeping accurate timing, because this chip uses a binary divider, binary counter inside, and the 32,768 can also be represented as 2 to the power of 15. So when using binary counter, we can precisely, based on the actions that this chip does, we can precisely count up to the second and get a frequency of 1 Hertz, which is exactly what we need for the clock to run. On the backside, there are no other components, so all in all, this is really a very simple module, but also very useful. While working on different projects, there are many occasions where we actually need an accurate representation of the current time, and that's most notable in situations where we need to take actions with our projects at the specific times or at the specific time intervals. So for example, if you want to execute a certain actions at 7 a.m. in the morning, then you would require such a module to be integrated with your project, and you want to keep the time. And also having the right time is also very important in situations where we do data logging. So we want to know at exactly what time what happened. It's really important in situations where we want to automate things, like in home automation, garden automation, and such. So one of the real and important reasons why this chip needs a battery is that it needs to keep the time even if the project is turned off. So running a code directly on the Arduino or in the Node MCU board here in this example, we can still use the internal clock and do some counting and do some time management to probably know some intervals and define some time periods, but there are a few problems with that. The most obvious one is that once the power is cut for whatever reason, then that clock will be lost. Here with this real-time clock module, we have a battery that serves as a backup for the internal clock to know to still keep the time. So even in the event if our main project or appliance is turned off and the power is cut to it, then the battery will still provide accurate timing. And these chips have such a low power consumption that a single 2032 battery can run them for up to 5 years. To connect this module to the Arduino, we will need 5 wires, and we first connect VCC and ground to the V-in and ground pins on the Node MCU, and this board can work on both 5 volts and 3.3 volts. So you can use it with Node MCUs, or you can use it directly with any Arduino board. And we need 3 more wires for communication with the board. The clock line is connected, in my case, to digital 5, to D5 input on the Node MCU. Then the data line is connected to D4, and the RST or the reset line is connected to D2 on the Node MCU. To interface the real-time clock with Arduino, there are several Arduino libraries that already exist, and for this example I will be using this Rtc By Makuna library that is written to be able to communicate with multiple real-time clock chips, and it also supports our, in the case, which is DS1302, and the example is basically pulled from the examples that the library provides, with the only difference that I've updated the pins that the library connects to. So in my case, I have VCC connected to VIN, I have ground connected to ground, then I have clock to D5, I have the data pin to D4, and the RST pin to D2. So in the sketch at the beginning, we include the required libraries. So the first one is the one that is actually doing the communication, and the Rtc DS1302 is the file that decodes decodes the data that's being sent from and to the real-time clock. And at the beginning, we specify the connection. We initiate the object with the correct pins that we used, and then we pass that communication object to the Rtc library so it can define the communication. Then there is a trick that's being used here in the library, so the code can know to set the initial date and time on the chip, and in this case it uses a special Arduino constructs date and time that define that are being set to the Arduino once the code is compiled. So we're first gonna display that to the serial monitor, and then we're gonna initialize an object with that date and that time. Next up, we check if the date time value is valid on the real-time clock, and if not, then we display an information that we are not sure that the date time is correct on the module, and we initialize and we call the set date time function to actually set the date. There are a few methods here that this code checks to make sure that we are actually able to write the date and time to the chip. It makes sure that it's running, and it does a check if we have time, if it's possibly older than what we have as a compiled in the node MCU, and if that's the case, then we also update it to the latest time and date that we have. Next, once we enter the loop section, we get the value from the real-time clock, and we print that value that we got. In the case if we don't have a valid date, and as you can see, a common cause that we don't have a valid date is either missing a battery, as in this case, or having low voltage battery, then we will also print out a warning so the user can know to replace the battery on the clock. Okay, so let's now try to connect all this. And first up, we'll need to add the battery in. And the battery pops into place, and I'll connect the node MCU to the USB of my computer. Okay, so now the USB is connected, and let me open up the serial monitor. So hopefully we should now start seeing the clock being updated, and I'll reset the board. So we now have what we have set initially when we compile the code. If I reset the board, we'll see now that the RTC is newer than the compiled time, and this is expected. So that means that the clock was actually running when we terminated this board. And to show that this is the case, I will disconnect the node MCU. So we no longer have power coming into the node MCU, but hopefully the real-time clock will keep the time while we are off, and this is what we basically want with our devices. I'll plug this in back again. Let's see if we need to restart the serial monitor. Probably. And I'll reset this pin. So you see that the compiled time that we initially set was at 7 AM and 47 minutes, but the real-time clock was skipping that time and it already passed 2 more minutes. So that's basically it for this example. I will soon have a follow-up video on this where I'll connect this this real-time clock module with an LCD, and also we will build an interface where we can get in and actually update the time through that interface, so we can keep it up and set something different than the compile time. And if you're interested in that, be sure to subscribe to the channel so you don't miss any of my future videos. Thank you for watching, and I'll see you all in the next one.